All right, let's get started. Mask up if you are in the class and not already. And we are going to be doing lecture 1E today, which is the introduction to the GA part 2, which gets us into the more specific details of the different genetic operators. So again, if you're in the class, please mask up. It's the ASU requirement. There's masks here. So, all right, so where we've been in is that we've been discussing, this engineering design problem where we've got this, so this is, I'll just write this lecture 1E, intro, GA part 2. So we've got our decision vector that we are trying to use this meta-heuristic to solve for. It's got a certain number of elements. This decision vector we can call a chromosome. Each component we can call a gene. So in this case, we have above here, this would be, so we've got N genes for a decision vector that's in Rn. And the genes you can think of as decision variables. And so the chromosome is just a collection of all the decision variables that might be of interest to you in an engineering design optimization problem. So if you were to choose a particular set of those variables, then we call that a strategy. And so a particular strategy I might denote, say, X vector sub A, and that strategy might, be particular numbers here, 1, 2.6, 8, -4, whatever. And that we would refer to as a genotype. And each one of those, we can think of each one of the decision variable instantiations as an allele of that gene, of a gene. And so we're going to then have an optimization objective that we're trying to optimize. So that optimization objective F and we might want to minimize it, we want to maximize it. There might be something that we want to do there, but that optimization objective we refer to as a character of a phenotype. And right now we're in the very simple case of single objective optimization where every phenotype just has a single character. And so there's kind of a one-to-one map between a character and a phenotype. But you can imagine we could have multiple characters, and in unit 3, we'll introduce multi-objective optimization meta-heuristics, in which case we will have multiple characters or multiple optimization objectives. So that'll be coming in unit 3. And then each value of a character, so if f of x is a character, if it equals, say, 4.6, this, for example, might be height. And this might actually be, like 4.6 feet or 1 point whatever meters. And so the actual value of the height is referred to as a trait. So you have a certain character, and then the values of those characters are the traits. And then you take those characters and you have to say, well, is this a good thing or a bad thing? Do we want to maximize height? Do we want to minimize height? And that all maps it into fitness. And so we have then that fitness function. And so let me just add a page this way. So then we introduce this notion of fitness, big F, and that takes on all of your characters. So if you had, F of 1, F of 2, and so on, then it combines all of those characters together to map them into a fitness function. But in our case, the simple case of a single character, it's just our single F of X. So maybe I'll even get rid of that subscript 1 there. And this fitness here is kind of a proxy for number of offspring. And so fitness functions are thus going to be non-negative. In fact, we'll say they're positive. So to map an optimization objective into a fitness function, you usually have to maybe add a little bit of an offset in order to ensure that the fitness function is always positive for every value of that objective. So yeah.
So the fitness function, basically that's what ranks how good the solution is?
Right, the fitness function is what will be used by the selection operator to decide which strategies get more representation in the next generation and which ones less.
So effectively, you do have a multi-character, I think it is, or multi-objective optimization.
Right.
All of that fitness function, you take the one, you're still kind of like optimizing just one thing that, like, you kind of turn it into a single function that you're trying to optimize.
Right. So the question was, well, and this is a discussion we'll have much longer discussion in Unit 3, but right, with multiple objectives, when you merge them together, in order for the algorithm to do its job, we need to somehow turn it into a scalar fitness to decide who gets more than others. And so, but there will be degeneracy in that there will be multiple ways to achieve the same fitness. And that's going to allow for a greater diversity in solutions that when we get than a single optimization. So we'll start seeing what's going to happen in the multi-objective case is we will see the emergence of a trade-off frontier where instead of your population all trying to approximate the optimal solution, your population will actually get stuck on a manifold, and that manifold will represent the trade-off between your objectives. And so some of those are going to be really good in one objective, but crappy in another. Some will be really great in the other objective, but crappy in the other. And so, and then that shape will actually be the output as opposed to a single point. And so then you'll be able to hand that shape off to someone and say, if you really like this objective, here's how much you can sort of trade one objective for another. So yeah, that's coming. So in our simple example, so like in the mini project, you could imagine a fitness function where you've got something like 40 minus F, and this would be a case where you wanted to, let's say that by maximizing capital F, your fitness, by maximizing your number of offspring, what you're actually doing is minimizing little f. And so this is how you might minimize little f. And then this 40 would be large enough to ensure that capital F stays positive. So this is hopefully going to ensure this will be greater than 0. Or you could imagine big F of X, or big F could just be simply F, or maybe F plus some offset. And so this would be the case where you want to maximize F, but you also added an offset to ensure this is greater than 0. Now, there are some selection operators that are just based on ranking, and we'll kind of go into that, in which case this offset's not going to matter. But there are other selection operators that really need this big F to be positive. And so in the ones that do ranking, it doesn't matter if you add an offset because the rank will be the same. In the ones that actually make use of this and need it to be a positive value, then we'll see that this offset will have an effect on the selective pressure. And so, so we'll see towards the end of here that, you know, that this term selective pressure is just another fancy way to say high phenotypic or fitness diversity. And like we said, if you have high selective pressure, what can happen is if you have low genetic diversity, then this thing will end up getting stuck in traps because you'll climb, or I mean, depending on if you're maximizing or minimizing, you'll end up getting into these traps where they're so steep that your optimization algorithm has no choice but to go down them and then get stuck at the bottom of these bowls and can't get out because it doesn't have enough diversity to get out. And so selective pressure is really great at finding local suboptima, but it's really bad at finding global because it gets kind of just focused too much on an area. So, and so we can control the amount of selective pressure by controlling things like how big this offset is in the fitness function. And we'll see stuff like that come up as we go into the selection operators here. So these are tools for us to manage this trade-off between drift and natural selection that we've been talking about so much. Okay, so, and I guess the only other thing I want to mention here is that this notion of fitness, for biologists, fitness is a measure of a population. So it isn't prescriptive, it's descriptive. And so for biologists, you go out and you culture a bunch of bacteria. This bacteria has this allele, this bacteria has this allele, and so on. And then after they all grow together, then you notice that, that one allele has dominated the population. And so you say that has higher fitness. And so you measure it afterwards. For engineers in engineering design problems, fitness is sort of prescriptive. And so in this case, the fitness is telling us how many offspring. So for biologists, we let the experiment run and then we count how many offspring and then we say, that's the fitness of this strategy. That's the fitness of this strategy. For in the engineering case, the fitness function tells us how many offspring are there. So it's kind of fitness first. So we end up putting in the particular strategy, X vector here, and then it pops out, well, that strategy is going to have 40 children in the next generation. Put another strategy, that strategy is going to have 10 children in the next generation. And so it actually tells us how many are coming out. So fitness is first in the engineering case. But you can kind of think that in the engineering case, F is sort of a proxy for running that experiment. So it's, whereas in the biology case, you actually have to, you have to inoculate the cell culture with the bacteria and watch it grow and then count how many come out of it. We're sort of doing that by putting in our vector into our optimization objective, into our fitness function. It's like the fitness function's running the experiment for us and counting how many offspring come out of the experiment, sort of the mapping there. So that's sort of the basics of how we turn an engineering design optimization problem into a fitness maximization problem with this kind of biological nomenclature. And now we just need to implement the GA, which will take all of this kind of biological background, will create an evolutionary system that is driven by all of this stuff. And then if we've designed our system well, natural selection, or artificial selection in this case, will be strong enough that hopefully we'll end up getting a dominant allele or a dominant set of alleles that end up doing a good job either maximizing or minimizing our optimization objective. Yeah.
How do you know from children each one should have each thing you're using the fitness function, but that's like, for example, just 40 months?
So the question is, how do we build these fitness functions to decide, how do you assign these number of children? And that is going to be dependent upon the problem. And so as we get into selection operators, we will kind of see that. But I mean, we don't ever know what kind of the right answer is, but the qualitatively, we know that if we want to maximize little f, then this fitness function, which is just little f plus an offset, maximizing big F will maximize little f. Now, do we need to simulate that a certain strategy has 40 children or 400 children? So in other words, do we need to scale this fitness by 50? Or do we want to actually maybe scale it down by divide by 50? And that's something that, again, is going to affect the selective pressure here. So if we have a hint that an optimization function has maybe a lot of local optima, then maybe we don't want so high selection pressure, because that's going to mean that if it finds one of these little local optima here, it's going to just sit there and loiter around that local optima, because the selection pressure is just going to be obsessed with the steep slopes of the optimization objective. So maybe in that case, we need to take this and scale this down. But maybe in other cases where there's a lot of shallow optimum regions, then in those cases, maybe it is okay for us to crank up the selection pressure so that in these shallow regions, they fine tune to find this lower point down here. So this is another reason why hyperheuristics become so important for these meta-heuristics, because sometimes you don't know what region you're in, and you need another layer of an algorithm that can play with how to scale this fitness function to best suit your particular optimization objective. And so I think that'll become more clear as we go into these operators. Question?
Would it ever make sense to make the fitness function also take in the number of iterations you're on?
So there's a question, would it ever make sense to have the fitness function take into account not only the genotype, but also say the number of iterations, which you might think of as the age of this particular genotype? And I would say yes. And when we get to multi-objective optimization, then we, at least in the readings for unit 3, I've put a reading on age fitness Pareto optimization, AFPO, that does a little bit of that, where it keeps account of the age of each genotype. And it turns out that by keeping count of the age and using it as an optimization objective, where you sort of want to say, like, what's the best for this age of genotype, what's the best performing one? And it keeps kind of a portfolio where it has old ones that are best performing and young ones that are best performing. And it turns out that you get solutions that kind of avoid traps a little bit better that way. So so there can be ways, and there are also additional strategies. One that I've put in the readings for this one that AFPO was kind of a response to, that try to keep that more focal. So there are advanced genetic algorithms that definitely do take into account age. They do it in different ways. So I don't say, this is the one way to do it, but it is sort of a thread that is interesting to tug on, and you can find literature out there that does that. Let me just make sure there's no questions online here. More chat. Okay. All right, so let's pile on forward here. And so last time I mentioned that, we're going to start the algorithm out. And the first thing we're going to do is generate an initial population. And there's a bunch of different ways we could do that, but we're basically going to, for simplicity, just draw a random, we're going to say, well, we have a population of M individuals with N genes each. And so we're just going to draw N random numbers M times, basically, to give us our N individuals and M genes. And depending on the range of each one of your genes, you might be able to do that in one step. So like if all of your genes are binary, for example, then you just need to draw a random binary matrix of an M by N binary matrix, and you've got your whole population. If some of your genes are binary, some of them are decimal and all that, then you might have to do things in a little bit more piecewise fashion, but you probably still can draw, do a kind of a vector-based operation to say, I'm going to draw all my M gene 1s simultaneously, all my M gene 2 simultaneously, and so on. So I'm just going to abbreviate all of that by saying that we have a matrix, that our population is just represented as a matrix that has M rows for our M individuals and N genes, or N columns for our N genes. So those are M individuals and M genes. And so this could be X11, X1N, XMN, XM1, and then everything in between. And so every iteration, I have to refresh this matrix. And so every iteration, I just have another N individuals, or M individuals and N genes, but I'm just changing what individuals are in that matrix. And so after my initial population, I am going to select R less than M parents based on my fitness F across all of them. Yeah. So the question is, can the number of genes vary with the individual? To start with, we're going to say that they don't vary per individual, but you can imagine, and as we get into unit 2 with genetic programming, you can imagine how different individuals might have different size genotypes, and there still has to be a way to turn the genotypes into fitness. And so if it's a simple expression, like a mathematical expression, then we probably want them all to have the same variables, so that we don't have to say like, which fitness function do you apply to, which function do you apply to, because then it gets a little weird. But when we get into like genetic programming, we will have a way so that we can sort of say something that's 2 lines of code can compete against something that's 100 lines of code. But for now, keeping it simple. Yeah.
The R, like let's say, like after I evaluate all the different 10 individuals with like the 10, the top, can I like sort it, make it top 10, and those would be the R, those would be like parents?
That is going to depend upon your selection operator. And so that's what we're going to talk about, the sort of 3 major selection operators that determine how you select those R. So the question was, do I just select like the top 10, or how do I select those R? And how you select those R is going to, again, it has to do with your selective pressure. How much pressure do you want to put on, how much fuel do you want to give the engine of natural selection? And so there are some cases you can kind of amp up selection, in some cases you can damp it down. And so those are the operators that we'll define. But in general, they'll all select a breeding population, or a number of breeders. And so you can think of that as, in our old generation, we had M individuals. So you can think of this as, there's M individuals here, maybe I'll write it this way. But in our new population, for the next generation, we are going to have a split where there's going to be R so-called parents, and the M minus others, and we can just call them offspring. So some of the parents hang around. The top performing parents stick around. You can think of the lower performing parents die off, and the kids of the top performing parents take their place. It's one way to kind of think about it. And so how we decide those are, that will go into the selection operators that we're about to define. After we select the R parents, we now need to figure out how to populate those M minus R offspring. So, so that's where we do reproduction. And in the reproduction step, that's where maybe I'll maybe put little boxes around here that's our initial population. This is selecting, and then now in our reproduction, this is where we do crossover and mutation. And so the selection, crossover, and mutation, I'll just make it 1, 2, and 3. These are all different operators that are degrees of freedom we have control over when we run a genetic algorithm. So we can choose different selection operators, whichever use the same selection operator through the whole algorithm, different mutation operators, and different crossover operators. And so we're going to talk about the most conventional ones of these today to plug into here.
So the selection operators, what gets you the R, and the crossover and mutation is what gets you the M minus R, right?
That's right. That's right. So the question for those online is the selection operator selects the R individuals, and the crossover and mutation find the M minus R offspring to pad that out to the full population. So that's how those things work. And then after reproduction, we got a whole new population. So then we can evaluate our termination criteria. Yeah, I'm sorry. R, for our purposes in this simple algorithm, R is a hyperparameter. It's set at the top of the algorithm and it stays. But you could imagine adjusting these hyperparameters dynamically. And we'll talk about that briefly here towards the end about ways that you can adapt to these hyperparameters. I've already talked about hyperheuristics, which optimize over the hyperparameter space, but still the hyperparameters within the GA are constant. There are other GAs that I'll mention here towards the end where hyperparameters like R can actually change over time. And those GAs will try to estimate population diversity throughout to sort of see, is drift taking over at this point? If drift is taking over at this point, I might need to increase my selection pressure. If drift is not taking over right now, maybe I can back off selection pressure so I can get a little bit more exploration. So we'll get back to this little diagram that I drew a while back here, but these adaptive processes help try to maintain us in this upper corner. And they do that by adaptively changing these hyperparameters. Okay, so then whether we've reached our termination criteria, if we have, then we report the last population and we end. Otherwise, we loop back up to just before the selection. And that's the basic outline of your basic genetic algorithm. If you were to build a genetic algorithm like on Mini Project 1 yourself, just keeping track of a matrix or an array or whatever data structure you want, these n individuals, and then constantly keeps modifying these n individuals in this particular way. What's the termination criteria? This could be, based on number of generations, could be based on convergence in fitness, could be based on diversity, genotypic diversity, etc. So there's a lot of flexibility in how you decide that this algorithm's over. The point here is that evolution is a process that never ends. So this can go on forever, but at some point you got to say, you're fine tuning and to the point where it's just not worth my computational budget. And so we're going to stop the evolutionary process and just take whatever you've got. And then you end up reporting, again, a population here. So you don't get one solution out, you get a population of solutions out, and also usually the fitnesses for each one of those. And so now the decision maker can look at these and say, well, maybe I'll just take the one with the top fitness. And that maybe makes sense. But there might be something interesting about these, and so there might be other criteria that aren't formally modeled in the fitness function, that of the ones that are top fitness, you can say, yeah, okay, I see that one of these is really great in terms of our optimization objective, but there's one that's not that much worse, and it's a lot cheaper for me to implement. And so maybe I'll use that one instead. So this population is actually a strength of these approaches because it gives the designer a bit of flexibility at the end. It sort of says, here's your top 5% or whatever solutions that we found. You choose among them, you're not going to do that bad. So it goes along with this idea of a heuristic. All right, any questions about this flow? The same flow we talked about at the end of last time, just a few more details. And then now our next step is to define the selection operators, the crossover operators, and the mutation operators, how to actually build those. All right, let me make sure there's no questions online. Questions online. Is it possible to have a different number of individuals per generation, or is it better to keep the population constant? So that kind of relates to, I think, an answer I just previously gave. For now, population size does not change, but you can imagine embellishments of the genetic algorithm where the population size varies as well. And that will, again, be an attempt to control how much drift you have in the balance between drift and selection. The other question here is, so bigger R means less selective pressure. Is that notion correct? That's a little more complicated to say a bigger R means less selective pressure. A bigger R means that you're more willing to keep the high performing individuals from the previous generation. And so you can actually, in many cases, that actually increases the selective pressure because those that do really well initially can just dominate. So high selective pressure means you climb fitness landscapes quickly. Anything that makes you climb a fitness landscape more quickly increases your selective pressure. If you are sort of giving it a different, the greater and greater bonus to previous high performers, you're effectively giving kind of a, you're adding selective pressure. So if I reduce R, then I'm reducing selective pressure because those who did very well in the previous generation don't get represented in their purest form in the next generation. If I increase R, then those who did well in the previous generation then keep getting additional representation. So I would say there's probably counterexamples, but for most cases, increasing R is probably going to increase your selective pressure than decreasing. But again, they're probably counterexamples. Question?
So isn't the offspring basically just small perturbations from the original R parents?
Well, we'll see that. So there are different mutation operators you could try. So some of those mutation operators are going to just randomly introduce new individuals that have no relationship to the parent. So we'll have, so basically there's sex, so there's crossover. So in short, what we're gonna see here is that crossover is gonna grab two parents here, and then it's gonna say, do these parents have sex? If they don't, then it has the option of just passing them through like clones. If they do end up having sex, then they swap genes between the two parents, and then there's offsprings that are combinations of those two. And so that will kind of be, so the crossover part. Now then there's then going to be room for some of the rest of those individuals to be added just totally randomly, as if they came in sort of from another subpopulation that was connected from elsewhere. So this has the flexibility for us to do kind of both of those things. All right, so let's get into some of those operators. All right, so there are, let's start with the selection operators. And this is for picking the R parents. And there are 3 common options. And these are attempts to control selective pressure. All right, so the first one and the most common is proportionate selection, or so-called fitness proportionate selection. So I'm going to put parentheses around here because sometimes the fitness is dropped. And this is also sometimes called roulette wheel selection, for reasons we might see here in a second. And in fitness proportional selection, we basically create a probability index of fitness, which kind of relates to like a softmax function for those of you in the kind of AI sort of side, but without the exponential. So the idea here is we create for every strategy. So we've got for individual K, we're going to define, I'll say for individual K, we'll define PK as the fitness of individual K divided by the sum of all the fitnesses. From J equals 1 to M. And so this, you can view this as the probability that K is selected as a parent. And so we implement this the same way we would in the stochastic simulation or stochastic sampling type approach, which is by drawing a random number. So we basically can, for individual K, we'll draw a random number, which I'll call RK. I hope that's not confusing the big R. Maybe I'll make it like little r K. And that's a random number which will be uniformly distributed between 0 and 1. So it'll be a number between 0 and 1, continuous number between 0 and 1. And then we ask, where does it land? And we put up kind of a dartboard here. From 0 to 1.0, where each segment of this linear dartboard has a length which is equivalent to the different PK lengths. And so we'll have like the first length here, this will be of size P1. Then we'll have maybe this will be P2, P3 might be larger, P4, P5, and so on. And because we know all of those add up to 1. So we can partition the line segment from 0 to 1 up like this. And then we ask, where does R fall? And if R, for example, falls here, let's say this is RK, then that's going to basically give a win to, and maybe I shouldn't have used K for this, but that's going to give a win to parent 3. So if we draw R random numbers, I'll say R random 0, 1 numbers, and then we can place them on here. And so on. Where they fall tells us who the parents are going to be. So, so if the dart happens to hit in region 3, we get a parent there. The dart happens to get region 5, we get, in his case, maybe 2 parents for region 5 and so on. So this is a way for us to decide of the R parents, how are they distributed across the individuals from the previous generation. So everyone from the previous generation, high fitness or low fitness, has a chance of getting in to the next generation, a random chance. But those that have higher fitness have a much better chance. Because if you have like super high fitness where you fill out this whole thing, and then everybody else is squeezed into this tiny little bit here, then those are individuals, almost all of them are going to be this one that has the large fitness. But there's still a chance that some of these will get into the next generation. So this is called roulette wheel selection, because you can imagine, if I were to wrap this around a roulette wheel, the kind of the area of the roulette wheel, as you got that ball following in there, like where is it going to land? Well, if I have larger sections, pieces of the pie, it's more likely to land there than those other ones here. So, dartboard selection, roulette wheel selection, that sort of thing. Question?
Is the total number of K's equal to the capital R for previously?
Yeah, so this, and again, so right, so there are R attempts to pick a parent.
And so this little number line is divided into capital R segments.
Well, no, M segments. So this number line has M segments.
Oh, right.
Because there are M PK values.
Well, you end up choosing capital R segments out of the total.
I choose capital R. I mean, I don't want to say choose capital R segments, because I can have multiple hits on the same segment. So like, if R is equal to 4, these 4 dots, I've got 1 hits 3, 2 hit 5, 1 hit whatever, this one is 6. And so then my 4 parents are going to be 3, 5 twice, and then this one.
Choose a segment twice, so,
yeah, I can choose a segment twice, and then that way it's another way that it can kind of be reproduced. So this is one way to do selection of those R parents, and it has high selective pressure. Yeah, go ahead. With the fan, I didn't hear all of that, but I heard you talk about recombination. Right. Okay. Yeah. So that's kind of what I'm about to get here. If one of the parents has high fitness, then or if 2 of the parents have high fitness or whatever, then they're very likely to get into the next population, which means you'll have very low diversity in the breeder population, and that may lead to very few changes if you do recombination from the breeder combination. So we'll get to the recombination here in a second. But yes, that's one of the consequences of, just in general, there's lots of interesting side consequences, but the big point here is that because the absolute value of fitness is taken into account here, then this is very sensitive to fitness. It has very high selective pressure. So in other words, if one strategy is just way better in terms of fitness than all the other strategies, then that one strategy is just going to take over. So that's what I mean by has high selective pressure. So it might be that we have one strategy that's excellent, and then the other 9 strategies are ranked so that the second strategy is pretty good, it's definitely better than the third, and so on and so forth. But if the 2nd through 10th strategy are so compressed in fitness that they are just dwarfed by the fitness from the first strategy, it doesn't even matter how different the fitnesses are in the other strategies, because they're not gonna make a difference. So this is potentially good, but it's also potentially overkill, because it gives so much, like we may really only care about the rank of the fitness and not the absolute value of the fitness. All right, so that's fitness proportionate selection. So before we go to the next one, are there any other questions about that? Is it pretty clear? This is, I think, one of the more straightforward version of the selection operators. Just randomly drawing based on a probability that is proportional to the fitness. Yep.
Last question.
Uh-huh.
The value of R should be equal to M, right?
The value of R should be equal to,
Migration should be equal to M, right?
no, so R is always less than M. I guess it could be equal to M, and then you'd have all breeders. But you want to leave room to provide new offspring. So, well, so there are heuristics for choosing R. And there are defaults. So all of the major, the GA, for example, in MATLAB, there's a GA the function, and they've already chosen an R for you. You have an option to change it, but their default's probably pretty good. And so there's a bunch of literature on sort of, what tends to be a good choice for R. And so maybe a third of your population and so on. Those would be great things if you want to experiment with in your mini project. It's again going to vary based on the optimization objective. And so I can't say all the time choosing 33% of your population is good for R. So it's hard for me to give you a great example there. You might have to do a pilot study of your optimization objective to determine, well, how much selective pressure do I want? So, okay. So that's fitness proportion selection. So then, yeah, question? Yes. So the question there was, for those online, with fitness proportion selection, can the same parent be selected multiple times? And yes, it could. And so really fitness proportion selection is sampling from possible parents based on a distribution that's set up by the fitnesses. And so we're not actually, it's not like drawing without replacement from an urn, where you pull in, grab parent A, put parent in the breeders, and then it's gone from the breeders. It kind of just sets up this roulette wheel, and the roulette wheel stays constant through the whole selection process. All right, now the second method is ranking selection, or you could say fitness ranking selection. Which was meant to be a kind of a way to say, if fitness proportion selection is way too high selective pressure for you, then here's an option that will really damp down that selective pressure, which hopefully will allow your GA to explore a little bit more before it commits to exploitation. So fitness proportion selection will get into those exploitation traps a lot easier. So you can try ranking selection. And the idea here is we rank our M individuals by fitness. And then we reproduce with copies that are proportional to the rank. So reproduce each with number of copies proportional to rank. And that constant of proportionality is a hyperparameter. So the idea is, when I say proportional to, I mean kind of inversely proportional to. So or I guess it depends on how you're ranking it. So, but the idea would be that if your best solution is rank 1, well, you're gonna have to think about how to do that, because you want them to produce more offspring. So if we were to rank things so that, for example, let's say the best solution, or the best strategy, we'll put in rank M, and we'll say the worst strategy, we can put in rank 1, and then we take this and we multiply it by some scalar. So we can multiply it by, I'll just say, some O, and then the number of offspring will be the rank times this O, which is just some constant, which for all intents and purposes, you can just pretend like it's 1. So in this case, the best strategy is going to put M offspring into the pool. The worst is only going to put itself into the pool. And then from there, what do? So then the third one is you draw uniformly from large population to get our parents. So this masks all absolute differences in fitness. So regardless of how much better the best strategy is to the second best strategy, it will work the same way. So this has far less selective pressure. So this really has damped selective pressure. So it promotes exploration. Yeah. Right. So so basically I'm saying, for example, you know, randomly permute. So randomly permute or order and take top, whatever top means, and take R individuals, or yeah, I'll say R top individuals. So basically, the best strategy comes out, you dump it into a data structure that has M copies of it. The second best comes out as M minus 1 copies, and all went through. So now you have a long data structure that has a whole bunch of copies of the best one, very few copies of the worst, and they're all in a line. So then I can randomly permute this thing so that I just randomly order these things, so that now if I start with index 1, I don't know which one it's going to be, a top ranked or a bottom ranked or whatever, and then I can just take from index 1 to index R. That's going to be my population. So I just draw randomly from them.
And you're more likely to have the really fit ones than those.
That's right. That's right. Question.
Making sure that there's no bias in the selections we are doing, or like, you know, since we are having multiple times M can be taken up, like maybe some segment is taken twice or thrice. How are we making sure that there are 3 or 4? They're not 3 or 4 segments itself.
So the question was, how do we make sure there's not bias? And I guess maybe I don't quite understand, and maybe I'm just missing something, but there's the idea here is, I mean, it's all kind of a deterministic process where the top ranked one is always going to have this many and the bottom ranked is always going to have this many, and then hopefully our random number generator that we use down here doesn't somehow favor some position or the other. But so long as we can draw uniformly, I mean, basically down here, this is just roulette wheel selection again, but I've just translated my fitnesses. I mean, this here you could replace with fitness proportionate selection, where your new fitnesses are just these ranks. And so, does that answer your question? I hope. Okay, great. I'm going to check if there's questions online. Okay. All right, so that's ranking, fitness ranked selection or ranking selection. The last one, oh yeah, sorry, go ahead. Well, if the term you're looking for was tournament selection, that's the next one we're going to go over, which is. Right, so we will, so the question was, you know, how does this relate to, there are these other terms you can see in the literature about elites, for example, and we will talk about that as we get into more sophisticated GAs for like multi-objective optimization, This GA, the R parents are a form of elitism, and that we're keeping those around, but there is a more explicit form of elitism where you take your top ranked individual, and even before you do your selection, you say, I'm gonna take so many elites, and I'm always gonna keep them around. And then I'm gonna figure out my breeders using one of these, and then I'm gonna figure out my offspring. I'm not adding any explicit elitism in this, but there are versions of the GA that have elitism. Well, so I would say that that fitness-based and reward-based, those are probably two synonymous terms. So ranking selection, then the last one that I want to talk about, so the broad selection operator to cover all the categories that you'll see in literature a lot is tournament selection. And again, these are all were driven by people becoming worried about the drift selection balance. So what the heck's tournament selection? Well, step one, select, and here comes another hyperparameter, select Y less than M candidates from our M population, our M individuals, to pick the best from the Y subset. And 3, repeat R times with replacement. And I'll say, so we can redraw the same one. And so Y can be used to balance diversity and selective pressure. All right, so imagine Y is equal to 2. In that case, what all I'm basically doing is setting up little tournaments, little fights between 2 individuals at a time. So it's like Fight Club. I look down at the M individuals and I say, all right, you and you, and I pull them out and I put them into a little fight and I say who wins. And how do I do that? Which one's got the top fitness? So of these 2 that I picked out, this one has the top fitness, and so it gets a spot. So I put it in the R parents, and then I put both of them back into the selection, and I redo that again. And so I do that over and over. Now, I don't have to choose 2. I could have chosen 10. And I'd say, all right, you, and you, get in there. They all go into a giant sort of mosh fight orgy thing, and then one of them comes out. And then that one ends up being the R parents. And then they all spent, get pushed back into the population, and we redo it all over again. So that's what we call tournament selection, why it's called tournament selection. And people like it because you can, this hyperparameter is a really good one in either promoting fitness advantages or demoting them. So if you set it low, then it kind of demotes fitness advantages because you can get into the, there might be one individual in the population with super high fitness. But if this is set low, then it's very unlikely that that individual is going to get chosen in a tournament. And so 2 other individuals will get chosen, and we'll look at their relative fitness, and then that determines whether they get in the R population. So if I choose Y equal to M, then I'm always going to take the one with the highest fitness. I'm just going to fill my breeding population with the highest fitness. If I set Y equal to 2, then I have a much better chance of filling it with diversity. So you can imagine low Y, like Y equal to 2, promotes breeder diversity, and high Y equal to M, promotes or increases selective pressure. All right, questions on that one? Yeah.
So like a lot of the times you're, sorry, I mean, it's really based on like the individual and how they perform.
Mm-hmm.
But in a trend selection situation, might there be times where you would actually want to take their fitness based on their like opponents as well, or
Well, so the question is there ever, does this tournament selection suggest an opportunity to make the fitness functions depend on multiple genotypes simultaneously? If I understand sort of the question. And I can see kind of where you're going with that. And there are probably special cases where, like in the artificial life community, for example, where that might actually be something that you'd want to do. For engineering design optimization, ultimately, we're going to hand off to our techs on the floor a set of parameters as a single genotype, and it sort of performs as it performs, regardless of what other hypothetical ways we could set it up. So it's one thing if we're trying to set up, like again, in the artificial life community, you might actually be trying to set up an ecosystem where you have multiple coexisting genotypes in a computer system. But in an engineering design optimization, especially for a single optimization objective, you're really ultimately trying to just find a single individual. And so fitness will always be based on a single individual. Any other questions? This makes sense. These are our three major selection operators. They are, I think, more interesting than the mutation and crossover operators. So I want to make sure we're all on board with these. Okay.
Just a quick question.
1 second, there's a question online. Yeah, go ahead, online.
Yes, regarding the statement with replacement here in the third step, I'm not fully following what is being replaced.
Okay, so the question online was what do I mean by with replacement? And that I'm just saying here that I mean we reinsert the Y individuals back in to M population before repeating.
All right, makes sense.
So the alternative with replacement would be to leave them out, and then you wouldn't have M anymore. You'd have M minus Y, and then you'd select from those, which we're not doing. We're just putting them back in.
All right, so they can repeat it. They can be selected multiple times this way. All right, thank you, sir.
Yeah, and so then the clarification online was that so they can be selected multiple times. Yes, they can. Then I thought there was a question in here. Yeah.
So the Y samples are, or the Y that you select random, right, from the population.
Yeah, I mean, so the number Y is a parameter you select at the beginning, but you select these Y randomly from the population. Yep. Okay. All right. Well, let's see if we can get maybe the crossover in before we finish today. Okay. So that's how we selected our breeders. So now we have to answer the question of who reproduces in the R breeders. And then also, and how? How do you have these genotypes swap genes? And so we do crossover, then mutation. And we're going to use a very conventional versions of crossover and mutation for a simple GA, but of course there are variants of these. So step one, select 2 of our parents at random. Kind of like tournament selection. And then 2, parents, these 2 parents, so parents crossover, and we'll define what that means. This is coming, we'll define what that means. So for now, we're just going to say they cross over with probability PC. And that is another hyperparameter. So that'll be something that'll be set ahead of time. And the crossover then produces two offspring in new population. Now, where does the mutation come into play? 3 for each gene in each offspring we want to mutate with probability PM, another hyperparameter. And then we can repeat numbers 1 through 3, or steps 1 through 3, until we have M minus R offspring. And then so our new pop will be the R individuals, the R parents, plus the M minus R offspring. And so now all we have to define is exactly what we mean by crossover and exactly what we mean by mutate. All right, so questions on this process? Yeah, go ahead.
Yeah, so there's a chance that even after the parents are selected, they might not select.
Well, so yeah, there is you pick these two parents and they might not end up so if they do not produce two offspring, then you end up picking another two parents. So
I mean, like, they might not be selected. Like,
yeah, oh sure. I mean, you select these two parents at random, so there is a chance that the two parents aren't selected. That's just the breaks of living in a finite population. Was there a question?
Yeah, so for number 1, selecting the parents, is that the proportionate selection, ranking selection, all that? Or we just went over it?
No, well, those 3 selections are what creates the R parents. And then so once we have them, this is an additional selection on top of that. Yeah. No, the fitness of the parents is what the question was. Should the number of offspring be proportional to the fitness of the parents? And if we're, naturally in biological systems, that's how we measure fitness. But this is kind of a non-biological mimic of the outcomes of biology. And so the idea here was we kind of did the numerosity first and then are selecting the identity second. So if that makes sense. Okay. All right. Well, let's see. I think we have 2 minutes, but I think I can at least do crossover here. So, so for crossover, again, this is the simplest version of crossover. We can have multiple point crossover. So we have crossover, and this happens again with probability PC. And there are multiple types of crossover. So there's 1 point crossover, and where we have, this is going to be imagine this to be, that's way too big. Imagine this to be the genotypes of 2 parents. So this is parent 1, this is parent 2. I will just maybe hatch parent 1. And maybe I'll dot parent 2. And so the way crossover works is you pick a point And this could be a randomly chosen point, or you could always say we're going to cross over in between genes 2 and 3. But then once you pick that point and you do the crossover, if you've determined the crossover is the right thing to do, based on that PC probability, then everything to the left of that point stays where it was. And everything to the right swaps. And so this will be offspring 1 and offspring 2. So 2 parents go in, 2 offspring come out with that swap. You can also do a 2-point crossover, and this is where I'm going to stop, where similar idea, but what we're going to end up doing is choosing 2 points, like here and here. So you could imagine you might get something like, actually, I'll just do this. So in 2-point crossover, you might say that we're going to swap these and swap these, but we'll leave the middle ones alone. So you can have multi-point crossover, and then you just can switch. Are we swapping? Are we not swapping? Swapping and not swapping every time you hit one of those fence posts. And those fence posts can be drawn randomly, or they can be set ahead of time. There's also uniform crossover, where we draw uniform positions. And this is me sort of just summarizing, I think, what I just said, and crossover. So the idea here is, again, those fences can be set in stone, or they can be drawn uniformly. And so you can just say, all right, every time I'm going to choose a new crossover point and swap. So we'll pick up where we left off here. All we have to do is a crossover, or maybe revise or revisit that next time, and then we'll do the mutation operator. And that will be the end of the GA. I'll be ready to move on. So if you have any other questions, happy to take those after class. I already kept you over those, so I don't want to keep you any longer. So we'll see you, whatever the heck day, Thursday. All right, so online I see, so the Y candidates, they're picked randomly to be inside the Y before entering the tournament. That's right. The Y candidates are chosen randomly from the M candidates to play a part in the tournament. You get a tournament winner, and then the Y candidates go back, and then you get a new random set of Y candidates after that. Any other questions online that I can take? Otherwise, I'll probably be ending the meeting. All right, see everybody on Tuesday or Thursday.